Hello friends, welcome back to my YouTube channel. Electricity is the lifeblood of our modern world, powering our daily life activities. Yet, behind its smooth and silent operation lies a hidden risk: electrical faults. These unexpected disturbances can strike in an instant, turning a stable system into a potential hazard. Today, we are looking at one of electrical faults, short circuit, and its impact on our power system. In this video, we will explore the followings. 1. What is short circuit, and how does short circuit occur? 2. Difference between overload and short circuit in our power system. 3. Effects of short circuit. 4. Types of short circuit faults. Under it, we will look at symmetric and asymmetric faults. 5. Three-phase fault and three-phase to ground fault. Which one is more dangerous? 6. How can we mitigate and protect our systems from short circuits? Now, get ready to unlock new knowledge. Stay tuned, let us explore this new knowledge. Welcome back. If you are new to my YouTube channel, please support the channel by liking and subscribing to the channel for upcoming videos. Thank you for your support. Before we start, it is important to know how current flows in a circuit. Electric current flows from live wire and return back through the neutral wire. However, when this electric current flows in unintended path, it becomes undesirable and hazardous to the power systems. This hazardous report leads us to today's topic: the short circuits in power systems. A short circuit is an abnormal condition in an electrical circuit where a low resistance path is created, allowing excessive current to flow. This usually happens when two wires in a circuit that should not be directly connected come into contact. For instance, when a live wire and neutral, or phase and ground come in contact with each other. They cause a large amount of current to bypass the normal load, causing overheating and damage of equipment. In simple terms, it is just like water in a dam that suddenly finding a leakage around a dam. It rushes through with high speed and causes damage. Short circuit results in an abnormally high current, known as short circuit current, flowing through the circuit. During a short circuit period, the voltage at the point of fault drops to nearly zero, creating a low resistance path for current flow. This can cause severe damage if it is not interrupted quickly. Since we have understood what short circuit is, it's important to differentiate short circuit and overload conditions. Here, an overload happens when the current exceeds the normal operating range but still follows the intended path. Whereas, a short circuit diverts the current away from its intended path due to a fault, leading to much higher current flow, and posing more immediate threat to system stability and safety. Although the current flowing through the overloaded equipment is high, but it still remains significantly lower than the current experienced during a short circuit. Now that we have exhausted short circuit, let us examine the causes of short circuits in power systems. A short circuit in a power system arises from abnormal conditions, which may result from either internal or external causes. For internal cause, they include equipment or line failures due to insulation breakdown in generators, transformers, or other components. These issues can come from aging, poor design, or improper installation. For external cause, these involve insulation failure triggered by lightning, overheating due to overloading, or physical damage, such as vandalism or accidents. As we have explored what causes short circuit, let us now look at types of short circuit in our power system. There are several types of short circuit faults, which are categorized based on the specific conductors involved. Below are the common types. 1. Single line to ground fault. It occurs when one phase conductor comes into contact with the ground. For example, a live wire touching a metal structure, or ground. It creates a low impedance path to ground, resulting in excessive current flow. 2. Line-to-line fault. Happens when two phase conductors make contact with each other. Example, a fault that occurs when two different phase wires touch each other due to insulation failure, or physical damage. It creates a direct path between two phases, leading to high fault currents. 3. Line-to-line to ground fault. A combination of line-to-line and to-ground faults, where one phase conductor touches both another phase and the ground. Example: a wire touches two different phase conductors and simultaneously makes contact with the ground. This type of fault creates a more complex fault current path, involving both phases and the ground. 4. Three-phase fault. All three-phase conductors come into contact with each other. For instance, a fault where all three phases short together due to severe damage or insulation failure. This is severe type of fault, as it involves all three phases and often results in very high fault currents. 5. Three-phase fault with ground. All three-phase conductors are involved, and there is also a connection to the ground. Example: a major fault where all three phases come into contact with each other and also make contact with the ground, such as when a transformer fails, or all broken lines touch the earth. This is the most dangerous type of fault and can cause significant damage to equipment and systems. The presence of a ground path added to the phases shorted result in highest fault currents. These can cause fire and system shutdown. Now, as we have understood all the short circuits faults, note that number 1, 2, 3 faults are called asymmetric faults because they did not affect all the phases at once, causing unbalanced currents faults. Then, number 4 and 5 faults are considered to be symmetric faults because they affect all phases equally, resulting in balanced fault currents. Since we have understood what short circuits are, let us delve into their effects on power systems. Here are the effects of short circuit on power systems. Number 1. Overheating. Excessive current flow during a short circuit can cause significant overheating in electrical equipment. This can lead to insulation damage, component failure, and reduced equipment lifespan. Number 2. Equipment damage. Short circuits can cause extensive damage to electrical equipment, including transformers. It causes winding damage and insulation failure. For generators, it causes stator or rotor damage. For circuit breakers, it damages contacts and cause operational failure. Number 3. Power outages. Short circuits can lead to power outages, affecting consumers, for loss of electricity supply, and industries, for production downtime, economic losses. Number 4. System instability. Short circuits can cause system instability, resulting in voltage fluctuations. It causes voltage sags or swells. Frequency deviations. It causes changes in system frequency. Number 5. Fire hazards. Arcing faults during short circuits can ignite fires, posing risks to people's life, and also to equipment, causing damage or destruction. Number 6. Reduced system reliability. Repeated short circuits can reduce system reliability, leading to increased maintenance costs, decreased system performance, and reduced equipment lifespan. Lastly, protection system activation. Short circuits can trigger protection systems, such as circuit breakers and fuses to isolate the fault. Generally, as we have seen all the drawbacks of short circuit faults, it reminds us the importance of designing and operating power systems with adequate protection and fault clearing capabilities to minimize the impact of short circuits. Let us now explore different methods to prevent or reduce their impact. Here are several effective methods to mitigate short circuits in power systems. 1. Proper system design. Use well-designed electrical layouts to minimize fault risk. Ensure equipment is rated correctly for expected loads and conditions. 2. Regular maintenance and inspection. Perform periodic checks on insulation, cables, transformers, and switchgear. Identify and fix wear, corrosion, or loose connections early. 3. High-quality insulation. Use proper insulation materials for conductors and equipment. Replace aged or damaged insulation promptly. 4. Protective relays and circuit breakers. Install and properly set relays and circuit breakers to detect and isolate faults quickly. Use devices that respond to overcurrent, earth faults, and other abnormal conditions. 5. Current limiting devices. Use current limiting fuses or reactors to restrict the magnitude of short-circuit currents. 6. Grounding and earthing systems. Implement effective earthing to safely direct fault current to the ground. Reduces the risk of equipment damage and enhances safety. 7. Surge protection devices. Install surge arresters or lightning protectors to prevent insulation failure from overvoltage surges. 8. Zoning and isolation. Divide the system into smaller protection zones. Faults can then be isolated without affecting the entire system. 9. Arc flash protection. Use arc-resistant switchgear and proper arc flash detection systems. Helps container eliminate damage from arc faults. 10. Training and safety practices. Training personnel on safe operating and maintenance procedures. Promote a culture of safety to avoid accidental faults. In conclusion, short circuits in power systems can have severe consequences, including equipment damage, power outages, and safety risks. Understanding the causes and effects of short circuits is crucial for designing and operating reliable power systems. Proper protection and fault clearing capabilities are essential to minimize the impact of short circuits and ensure system stability. Here is the end for today's session. If this video is helpful to you, please support the channel by liking and subscribing to the channel. Thank you for watching. I will see you in next video. Bye.